So what is energy? It's actually this kind of really weird question, right? We talk about it all the time. We have this sense that we know what it is. But the definitions are a little bit weird, right? It's the capacity for doing work. What does that mean? Does that mean that you're just really smart, you have a lot of energy? What is this capacity for doing work? Well, you have to go back to the history of the science of energy and what they were trying to measure, which was they had just started developing steam engines. They had just started the Industrial Revolution, and all of a sudden they had these things that were doing work, and they wanted to figure out, how can I figure out how much coal I need here to make the axles turn and make the looms weave fabric? How do we do this? So they needed some measure. They ended up coming up with this force times distance. Okay, so what's this force? Well, there's gravity, it's a force, right? And so if you drop something, the distance that you drop it, that force is, there's a Newton, which is the force of gravity, right? So a Newton meter was the force, and then the distance is, is the meter. So Newton is the force, the distance, so it's force times distance. And James Prescott Joule came up with kind of an interesting device, which is what's shown here. So you've got this weight that's going to drop 1 meter, or whatever he measured it, how far it was dropping. And he had paddles that were going to spin, so it's attached by a string, and it spins these paddles in some water. And then he's got a thermometer measuring the temperature of the water. And what he found was when he did his 1 Newton meter, right, and dropped the force times this distance, he raised the temperature of the water, which means that energy comes in more than one form, right? There was this potential energy when it's sitting up here and he hasn't dropped it, and then he drops it, and it's mechanical energy, it's turning that spindle, which is what they were really interested in back then, but it's also making heat in the water. So energy is heat, and it turns out that 1 gram of water is raised by 0.2, so like a quarter of a degree Kelvin. Everyone familiar with Kelvin degrees? Yep, okay. They are basically your Celsius degrees, but they go to absolute 0. So that way you don't have to worry about negative numbers. So a joule, named after James Prescott Joule, is equal to 0.736 foot-pounds, and that turns out to be really, really small, right? A 0.003 watt-hours. So that's how we can understand it in terms of force, in terms of the ability to do work, and there's obviously this relationship, because then you have heat energy. If you can raise, 1 joule raises 1 gram of water by that 0.24 Kelvin. So there's a reason we use British thermal units, and that's because all of this science was done by British scientists because they started the Industrial Revolution and were the ones burning all the coal. So BTU is a British thermal unit, and it's the heat to raise 1 pound of water 1 degree Fahrenheit. Notice we're now in imperial units. How many people in the room can tell me, could take their arms and say, I think this is about a meter? How many people can take their 2 arms and say, I think this is about a foot? So we're Americans, and we have an intuitive sense by living in our culture of about what a foot is. And how many people, if I tell you it's going to be 80 degrees outside, you know what clothing to wear? How many people, if I tell you it's going to be 23 degrees Celsius outside, you know what clothing to wear? Fewer. I'm glad to see so many. This is an improvement. It's a battle that's been waged since long before I was born. So we also measure heat energy and energy in general in calories. And this was the heat to raise 1 gram of water from, and this is now in Celsius, from a very specific degree Celsius to another one, but basically 1 degree Celsius. And there's a relationship between these. So 1 BTU is equal to 0.25 kilocalories, which is equal to 0.2931 watt-hours, which is equal to 1,055 joules. The point is that these are all things you can translate from one to the other. There's a relationship. Yes?
On screen before, the first equation that involves calories, is that kcal as well?
No, that's
Single
single calories. We're actually going to get some. We're going to do a little calculation later in class, and that's going to be important. So I'll get to it now. The calories that you count on on your food labels are actually kilocalories. This metric unit of calorie is used in by chemists working on very small scales to measure a very, very small amount of energy. So when we look at food, we have to use kilocalories. So that's worth knowing because you've got to get the right order of magnitude. So there are a bunch of forms of energy. Again, this should all be reviewed. But there's kinetic energy, energy of motion, so this is mechanical energy. We have thermal energy. We're going to spend a lot of time thinking about that because heating and cooling are issues. Then you have chemical energy, so that's all the energy that's stored in fuels. Electricity is essentially electrons carried through circuits. Nuclear energy is the energy in the sun, and obviously we can split atoms and make nuclear energy, or make heat, turn it to heat energy and boil water. And then we have potential energy, which is, you can think actually that chemical energy is a form of potential energy until it's actually released, until you break bonds. But it's the energy typically stored from the whole floor height. So dams with hydroelectricity, they're storing potential energy. You can actually say how much energy is stored in the dam based on the height of the dam and how much water is behind it. So just to kind of rehearse it and make it clear. So we have what type of energy is in the sun? Nuclear energy. And now it's shining on a plant, and what type of energy is that? So it's, well, first it's light energy, so that's a form of energy, is light. And then it goes into the plant. Oh, sorry, I forgot that I was going to talk about the fact that it's not only shining on the plant, it's transformed into heat energy, actually the vast majority of it. Does anyone know how efficient plants are at converting light into energy? You know what their efficiency is? Yeah. The efficiency of photosynthesis, do you know? Like if I have 100 units of light energy shining on a plant, what portion is turned? Yeah.
1%.
1%. It's about 1% efficient. So the whole world has run on solar energy at starting out at a 1% efficient conversion. And at every level, every conversion, right, you're going to lose energy. You're going to be less efficient as the whole system goes. So that's something to think about when you're thinking about biofuels. But yes, so somebody said chemical energy earlier, and that was chemical energy. Okay. So now, there's a banana growing on the tree. What type of energy is there right now? Did someone say potential? Yeah. How's it potential energy? Two ways. One, it's chemical energy stored that hasn't been released. The other way is it could fall, right? So now this guy eats it, and so we have chemical energy, and it goes into the guy and he turns it into mechanical energy and heat. You notice heat shows up everywhere because heat is basically what happens to the waste. So here we've got a cycle of energy conversion. We have potential energy as the guy leaves off the cliff. Kinetic energy as he's falling and as his body is shifting. Mechanical energy is the shocks absorb the impact, right? And has anybody done any mountain biking? Right. Have you ever felt your shocks after like a pretty rough ride? It's really hot. So that's a lot of mechanical energy that's being converted to heat energy. It's absorbing the fall. and then heat. So the way, the big concept that came out of all of this stuff that these British physicists and engineers were studying were the laws of thermodynamics. And the first law is that energy is not destroyed or created, it is simply transformed. So that's why there's all that heat, right? That's what happens when you transform the energy. It's not going away, it's turning from one form into another, and that form is heat. The second law, though, says why it happens that way. This process is not reversible. There's only one direction with the thing. I realize there's a pop culture reference there. There is always waste in any energy transformation, so nothing is efficient. So the plants, the photosynthesis, 1% efficiency. All the rest of that light energy is turned into heat energy or reflected back, changed into some other wavelength of energy. Everything goes from high concentration to low. This is this idea of entropy, right? So from high quality to low quality. So high quality energy would be something like electricity. Low quality energy would be something like heat. And there you go, from high temperature to low. So this is going to be really important. Which way does heat go? Hot goes to cold. If you know that, you'll never be wrong, except when you do something interesting with mechanicals. From high potential energy to low. So something has high potential energy when it's on top of the cliff, and when that cyclist lands on the bottom, he has much lower potential energy. He's used it up and actually put it into those shocks. And also from high pressure to low. So if you have something that's, and this is related to high concentration, right? So high pressure, this is going to be really important when we think about airflow. So airflow through a building, we know which way the air is going to go. It's going to go from high pressure to low. And it takes a lot of low entropy to make even lower entropy. Remember, low entropy is higher quality. So for instance, if we have sunlight, which is very, very high quality, so a very low entropy source, but it's very diffuse, so that by the time it hits the Earth, as heat, you know, it would take a lot of concentration. So anyone ever seen like those power towers, big fields of mirrors shining sunlight onto a concentrator? You've probably seen images of those. So that's an example of where you're taking a lot of low entropy to make even lower entropy, right? So you're taking light, which is diffuse, and concentrating it as heat, and it takes a lot of it to concentrate it to get the heat high enough so that you can actually, in this case, boil salt to boil water to turn a turbine and make very, very high quality energy, very low entropy electricity. So there are two concepts that come from this second law. Remember I said that energy can't be destroyed? So how come we always talk about using up energy, right? We always say, well, we're using it up. We can't, right? It can't be destroyed or created. Exergy is a way of describing what can actually be used up, right? It's a way of really thinking about what we're actually using up, which is the available energy, the energy that's available to you to be used for a particular purpose. So it accounts for the irreversibility of the process. So that's something that comes from the entropy law. The other idea is emergy, which says, okay, we've got this stock of energy. We know we're not destroying it, but we've got to account for all the different qualities that it degrades into. And if we know about those, we can start to map our energy systems and say, for this purpose, this energy quality is appropriate. But for this purpose, this would not be the best use because I have some lower energy quality energy to use, so lower emergy. And by putting them all in these constant units of emergy, that's a way of thinking about it. So I'm not going to ask anybody to do what's actually some pretty tough math with these two concepts, just to know that they exist, and that when you think about using up energy, you're actually talking about transformations.